anonymous results. So I am not aware of the general level of exposure of the audience. So it like some people might feel a bit coddled by this talk, and others might feel it's a bit too advanced. So let me know, and I'll try to work out like individually. Yeah. So yeah, before we start, I'm going to start basically an example. So me and my friends have gone shoplifting, and we have stolen something and gotten caught on camera. We want to get away with this shoplifting, and we also have some hacking skills, and we wish to delete the files in the government servers that pertain to our case. We were caught on camera, there's a recording of us, and we want to delete the files in the government system. And the way the government organizes these files is in a standard file system. So there is the government's own mainframe, which is connected to several servers. And each of them has various folders pertaining to their departments and sub-departments. And somewhere deep in their file structure, is our recording. And we want to get in there and delete it. Now, the government, of course, has a lot of contingencies in place to prevent us from doing this. The first contingency is actually something that you'd be familiar with if you worked with file systems before, say, the 2000s, where in order to delete a folder or something, you have to delete all subfolders and subfiles first. So you always have to go bottom up. This used to be done mainly so that you weren't left with dangling references, but that's not the point. The point is the government's first contingency is that you can only delete bottom up. So meaning that our file, my file, for example, which is server 1/magic/shoplifting/eyeshadow/dia, I have to delete from there. And if I want to say delete the entire shoplifting folder altogether to obscure what I've done, I'll need to delete all 4 of these files and then all the files under shoplifting as well. I can only delete bottom up. The second contingency, which is a bit more disastrous, which is if I delete some file, say my own. So firstly, this is just an animation of me deleting things bottom up. Never mind. But second contingency is that if I want to delete any file, say my own, then the folder that I've just hit, say eyeshadow in this case, will be copied so if I delete it there, then the entire folder gets copied into the shoplifting directory, eyeshadow 1, eyeshadow 3, and the number of times that this copy is made is completely up to the government. They can make 5 copies, they can make 1,000 copies, they can make 1,000,000 copies. They just pick whatever number they want. They order extra servers if they need to. They just make as many copies as they like. Now we're a bit screwed because this means that even though I've just deleted my folder, my file, the recordings and the case files corresponding to all my compatriots, Julia, Sylvia, Susan, they're still there, and they've been copied now 5 times. And now we have to go about deleting all of them individually. And again, when we delete them, the government can perform this operation all over again and start making more copies. And every time it could choose to increase the number of copies it makes, or go up, go down, pick as large a number as they want. So we're in hot water. What do we do? So the Hydra Theorem, which is the combinatorial game that someone was talking about in the chat, is this basic exercise where you're allowed to delete one file at a time from the bottom, and the government in response is allowed to copy the folder as many times as it wants. And the number of files and directories gets very big very fast. The reason I'm mentioning this is that this is one of a lot of people also use this as notation for large numbers. So, for instance, if you fix some strategy for the government, the number of files in the entire file system gets so large so quickly that you can use a number that is astronomically large, number that is larger than the number of atoms in the known universe, number that is useful in some combinatorial theorems or whatever. People, they want shorthands for large numbers because it's preferable to writing them in, say, exponents or whatever. And while it's getting this large, we are only allowed to delete one file at a time every time we do this. And the reason it's called the Hydra Theorem is because of the legend of the Hydra, which was a multi-headed beast in Greek mythology, and I think Hercules was tasked with killing the Hydra. And every time he chopped off a head, more would grow in the same place, which is similar to the. I'm sorry, there's some noise from outside, which is similar to the copying thing that the government does whenever we delete a file. Which is why it was named this. It was the original paper that discussed this, phrased it in terms of the Hydra, and in terms of rooted trees, which is something we'll get to in a second. It was a paper written by Kirby and Paris. I prefer to think of it as having been written by the pink alien and the city rather than two random white dudes, because it just makes it more interesting. So in this paper, they discuss how in this game, not only can we eventually delete all record of our theft, we can in fact just keep going and delete the entire file system whatsoever. No matter how complex the initial file system was, no matter how many directories or how much storage the government has, just going one by one, we can erase the entire, all the servers that the government has. Which is saying a lot if you think about it, because it's saying that no matter what the government does, which is quite a lot of power that the government has to create more storage, we will still erase everything. Why is this happening? And what does this mean? So before we get into a bit more of the how, what I want to say is that the reason this is happening is because every time we erase something, we change the structure of the file system. For instance, if every time I deleted, say, my own file, the government put another file in the same place, then the structure will go back to normal. As in order to delete something, I would need to delete that file again. And if the government put another file in the same place, I would just keep on doing this forever. I would never win. However, the way we phrase the problem, the government is sort of using this greedy algorithm where it says, this folder is the most vulnerable because it just had something deleted from it. So I will copy this folder because it seems vulnerable to me. That the copying of the folder rather than putting another file in the same place is it changes the structure of the tree, and it sort of makes it simpler because all the complexity that you're increasing happens further up. The copying that you're doing happens further up than where you deleted it, where you deleted the file. So and the idea is that because this complexity of the tree, whatever we mean by complexity of the tree, always decreases, eventually we should exhaust all that complexity. So first of all, I'm going to start you off with some terminology that if you're going into logic or set theory, you should be aware of. Linear orderings are just orderings of things in a line. They are orderings where for any two elements, either one is before the other or one is after the other. And well orderings are essentially linear orderings that only go in one direction. So they are linear orderings where if you try to walk in the leftward direction, you will eventually hit the beginning of the order. This is similar to, for example, the natural numbers. The natural numbers go 0, 1, 2, 3, 4, 5, 6 in one direction. And if you try to walk backwards, you will eventually hit 0 in finitely many steps. The steps can be whatever you want. You don't need to go n minus 1, n minus 2, whatever. You can jump over multiple. But you will eventually still hit the beginning. But there are more complicated examples of this. For instance, here, this is on the real line. Here, 0.9, 0.99, 0.999, and so on, up to 1. Then even here, if you take finitely many, but you can't keep walking in the leftward direction infinitely long. For instance, even if you start at 1, which does have infinitely many things before it, if you try to take a leftward step, you would have to skip over infinitely many of them. And if you'd land at some 0.999 finitely many times. And then you'd have only finitely many steps left until you hit the beginning. The reason this all happens is because all the accumulation that is happening here, 0.9, 0.99, 0.999, the accumulation that happens only in the rightward direction. For instance, if you had 0.01, 0.001, 0.0001, if it were accumulating in the leftward direction, then you'd be able to take an infinite walk sideways, like in the leftward direction. You'd be able to go 0.1, 0.1, 0.01, 0.001, and so on. Because there is no accumulation in the leftward direction in this ordering, it's a well ordering in the sense that you cannot take an infinite walk leftward direction. Now you can sort of start to see where I'm going with this in terms of the original problem. The idea is that if we take the structures of trees, if we take the structures of the file systems that we're working with, and we arrange them in a well ordering, where the entire process of us deleting a file and the government copying things makes the tree structure simpler, meaning it goes left in the ordering, it decreases in the ordering. Then in finitely many steps, we will exhaust the tree, meaning it will hit the simplest tree, which is just one node. That is the general idea of the proof. So before that, what do I mean by tree? A rooted tree is just some arrangement of files in our file system. It needs to have a thing at the top called the root, and everything else emanates from that, the way that a file system is organized. So you have folders underneath it and subfolders and so on, and at the end you have files. These are just various rooted trees. And the idea is that we want to order rooted trees in the order of their complexity, whatever that means. I'm not telling you what it means yet. We need to order them so that when we delete something from the leaf, a file from the file system, and the government does the copying thing, it becomes simpler, a less complex tree. And we need for this ordering to be a well ordering. And the way we do this is by using something called ordinal arithmetic. Now, ordinal arithmetic is a thing that logicians and set theorists enjoy using. It's a way of manipulating well orderings in a consistent manner. It allows you to manipulate well orderings as if they are numbers. That's why arithmetic. It allows you to take, say, the infinite well ordering we talked about earlier, 0.9, 0.99, 0.999, up to 1, and you can give it a name. The name will be omega plus 1, but we'll get to that later. So using ordinal arithmetic, we want to put the trees in a well ordering so that the entire process of file deletion followed by creation of copies decreases the position of the tree in the well ordering. And therefore, eventually, we'll have to win. We'll eventually wind up at the beginning, and the government will lose all its files, which decidedly takes revenge on the despotic system. No, never mind. We will always clear of all files and folders. And before I get to what the actual proof is, it should be noted that coming up with this proof is a bit hard. The general gist of the proof is fine. The idea that you should be arranging them in some order so that each turn that we play, each move that I make and each move that the government makes reduces the complexity until there is no complexity. That is a fairly standard argument. That's something that one can do. Coming up with what the well ordering is for trees, what it means to well order all the trees, is complicated. It's complicated for a very specific reason, and that reason is that this theorem, this well ordering of trees, is independent of Peano arithmetic. Now, what does that mean? Okay, so Peano arithmetic is it's a set of axioms. Now, an axiom is okay. So I don't know if the audience knows what axioms are. So if somebody has a doubt about what axioms are, I think. Oh wait, yeah, okay, yeah, okay. So okay, basic truths. Okay, so fine, yes. Now, I would prefer to say basic assumption because truth is abstract. It's deep philosophically speaking. Axioms are what we would prefer to have at the basis of our reasoning. Yes, and Peano arithmetic specifically wishes to capture what we can do with natural numbers. The idea is that Peano arithmetic comes with rules for how you compute multiplication and addition. And it comes with something called induction, which I'm hoping all of you are aware of. Like, you prove something for n equal to 0, then you prove that it holding at n implies it holds at n plus 1, and therefore you can prove that it holds for every natural number by going, f0 implies f1, therefore f1 implies f2, therefore f2, f2 implies f3, therefore f3, and so on. Yeah, that's the underlying principle of induction, and it's a very strong principle. It's a very complex principle. So much so, in fact, that I think every result in number theory that the audience has come across to this point is proved within Peano arithmetic. For instance, if you've come across the four squares theorem, the theorem that every integer can be written as the sum of 4 squares, that can be proved in Peano arithmetic. If you've come across almost any result in graph theory, that can be proved in Peano arithmetic by adequately assigning numbers to the graphs and using the tools given to you by Peano arithmetic. The audience may not have done much theoretical CS, but if you do theoretical CS, virtually every proof that you do can be done in Peano arithmetic. Entire disciplines have risen and fallen entirely within the confines of Peano arithmetic, is my point. It captures a very powerful tool for doing finite reasoning. So it allows you to reason with objects that are finite. Using induction. The reason I'm stressing so much on reasoning with objects that are finite is because the traditional foundational basis for mathematics, which is ZFC, if you take the assumption that there are infinite sets out of it, you get Peano arithmetic. As in, if you are allowed to reason with anything other than the assumption that there are infinite sets that you can work with, that you can use as tools, you get Peano arithmetic. So it's a special system. It allows you to reason in almost every way that we know how to, purely within the finite, without assuming that there is anything infinite. It's the basis of all finiteistic reasoning. It's a standard catchphrase. So the axioms I've listed here, they're not exactly important. They're just the defining axioms for addition, multiplication, and the induction schema. Yeah, sorry, I just like making memes for this. Okay, so now the bonus content. So I got there fairly early, but the point is, yeah. So the way we get to this proof is by allowing ourselves to talk about the infinite concretely. This is why I like this proof so much. So before that, firstly, what do we need? How exactly is the well ordering constructed? What do we need from the well ordering? So similar to, so the idea is to assign numbers to the trees, right? So as that's the traditional manner for constructing, for putting things in order. You give them numbers so that the higher the number is, the more complex the tree is, or the lower the number is, the less complex the tree is, something like that. So the traditional convention is that the simplest tree, one node at the top to one node under it is one. We assign one to it. And if we want to merge tree, so this is I'm just making some guesses, some educated guesses, so that we can get to the actual content of this proof. If I've assigned T1 to one tree and I've assigned T2 to another tree, and I want to merge them via the roots, like at the root, if I merge them, I'm just going to assume that the number I assigned to the composite tree is T1 plus T2. This is an educated guess. There are other versions of this proof that do not assume that they are additive. But that's not the important part. That's the thing. What is important is something I like to call the alphabet move, which is if I have a tree and I put a root above the root of T, and I join the root that I put above to the root of T. So it goes from T to point joined to the root of T. I call this the alphabet move because this is what Google did to become Alphabet. So Google was initially what the corporation was called. Then they created the Alphabet Corporation and became its subsidiary. So you create a root above the root and you connect it to it. So I'm going to call this the alphabet move. Now, what this does to the number we assign to T, I don't know yet. I'm not defining what we do yet. It's just some function L of T. It just does something to it. We don't know what it is. We will find out what L should be by looking at the requirement that we have on the number. Now, what was the requirement that we had? We wanted for the well ordering to be such that when we delete a file from the file system and the government finishes copying that folder as many times as it wants, the whole number should go down. The only requirement on LT is that the number should decrease at the end of this move. So that means that, if initially you had some X folder something tree and a file there, and I deleted that file, and then the government copied the folder, I should be left with a smaller number than I had at the beginning. So I'm going to give you an example with what we had at the beginning. So this is a small part of the tree we had at the beginning. Can any in the audience guess what would be assigned to this tree using the function L and the addition that we defined? As in, what would be the number assigned to this tree? For instance, if I've given you the base case, which is that dot is 1, and I've given you the function L, which performs the alphabet move. How would you construct this tree?
Like L of 1 plus L of 4 maybe?
Yes, exactly. Yeah. So the 4 nodes, Julia, Sylvia, Thea, Susan, joining them together is 4 at the top, at the eyeshadow point. The switchblades folder is 1. It's L4 plus L1. So This is L4 plus L1. When I delete the DA file, it becomes L3 plus L1 for the same reason, as in there are now three files over there. And then the government takes the entire eyeshadow folder, just the entire triangle over there, and copies it some n times. We don't know what n is, it just copies it as many times as it wants. And the effect this has on the number is that you literally multiply L3 by n, meaning you literally take a bunch of L3s and you add them, n of them. So you get L3 times n. And we require that the number at the end be smaller than the number at the beginning, meaning, and the L1 is not doing anything, the L1 is just there. So what we need is that the L4 part be bigger than L3 times n. Or in general, we need that LT plus 1. The T plus 1 means we've added one file, if you know what that means. So, and should be greater than LT times n, which is a bit of a tall order because n could be anything. Whatever number we are assigning to LT plus 1 needs to be greater than LT times any finite number, which is asking for something a bit drastic. How do we? Okay, so firstly, I want the audience's guesses as to how we get around this problem. Because like, as in, there are no right answers. There are no wrong answers. Sorry, there are right answers. There are no wrong answers. Please feel free to take a guess at what the function L should be to satisfy this property.
You can't use them over the reals or something because
I'm sorry?
you can't L can't be over the reals, I think, because you can make the finite
Yes,
number.
that's true.
Uh,
That's true. Firstly, yeah, exactly. So it can't be over the finite numbers, or it can be the zero function, but then it wouldn't accomplish what we're trying to accomplish. But yeah, it can't be over the reals because whatever LT is, we can multiply it by a sufficiently large number to make it greater than anything. Okay. So it needs to do something different. Okay, I'm going to give you the answer, and it's going to be really stupid sounding, but what if LT plus 1 is just LT times infinity, meaning it is greater than LT times any finite number? Now, that sounds incredibly stupid. Um, but the point is that, okay, I know that going through school, people are taught to be a bit afraid of the idea of just using infinity wherever they want. There is a reason for this. It is a very tempting construct. People tend to make mistakes left, right, and center if they are working with infinities. But in the olden times, when people were not as afraid of the idea, people would work with constructs like this, and they are in fact very useful. And that tradition still remains if you are a set theorist. Specifically, we write infinity as omega in this case because we don't want to be tempted by it. And we use a specific well ordering. Namely, we use the well ordering I've just shown you on the screen, where omega sits at the end of all natural numbers, and then you just continue. Meaning you have omega plus 1, omega plus 2, omega plus 3, and so on, until you reach omega times 2. And then you continue omega times 2 plus 1, omega times 2 plus 2, and so on, until you reach 3 omega, 4 omega, and so on, until you reach omega squared, omega cubed, and you continue. Now here it says it ends at omega to the omega, but no, it just continues. It will keep going, omega to the omega to the omega, and so on. Here also is that all the accumulation happens in the forward direction. the accumulate, for example, if I'm trying to go backwards from, say, omega plus 1, I will go back to omega. Then I will have to take a step down to some natural number, because there is no omega minus 1 in this ordering. It just, all the natural numbers happen, and then there is omega. Similar to the 0.99, 0.999, and so on up to 1. So when you take a walk backwards, you will have to drop down from omega to some finite natural number and then walk back. So this is also well ordering, even though it's a bit harder to see. And here we do have objects that are bigger than any finite natural number. That is the crucial part. Here, these are called the ordinals. The ordinals that I talked about earlier, ordinal arithmetic. These are the prototype of all well orderings. All well orderings are sort of built from ordinals. And the function that we need is omega raised to the power t, where, this ordering describes what omega square means and omega to the omega means. And the function that we need is omega to the power t, which will, of course, if you take omega to the power t plus 1, it will be omega to the power t times omega, which is greater than omega to the power t times any finite number n. That is the purpose omega serves here, basically. And now we have the right function for our proof. Setting L equals omega to the power t. And once we have that, our proof is complete. It just, you assign ordinals to trees using our numbering. Deletion and copying decreases the ordinal for the reason that we saw, because LT plus 1 is greater than LT times any finite number. And the ordinals are still a well ordering, hence all the files are deleted in finitely many steps. Now, that is the proof of the Kirby-Paris theorem, the Hydra theorem. It shows you why you will always win against the government, because it shows you that there is a way to measure the complexity of trees, specifically using ordinals, that decreases every round you have. But can we also construct this ordering using natural numbers alone? Yes and no. So, for instance, the ordering 2 omega, 0, 1, 2, 3 up to omega, followed by omega plus 1 plus omega plus 2, omega plus 3, and so on up to 2 omega. You can think of this as an ordering that extends past the natural numbers, or you can think of this as a slightly wonky ordering on the natural numbers, where you have 0, 2, 4, 6, 8, and so on. And after all of those, 1, 3, 5, 7, 9, 18, and so on. Right. Can you reorder the natural numbers so as to mimic this ordering? The answer is yes. You can, because this ordering involves only counting. Yes, you can in fact reorder the natural numbers so as to be in this shape. I'm going to use the word shape, even though it's a bit not correct. But you can reorder the natural numbers to be in this shape. And so then the question arises, why can't we just use that varied shape of the natural numbers to reconstruct this proof entirely using finite objects, things that do not go beyond the natural number line? So this argument that we have just put on the screen, assign ordinals to trees via numbering, that part can be done in Peano arithmetic. Deletion and copying decreases the ordinal. That part can also be done in Peano arithmetic. The ordinals constructed like this, a la well ordering, cannot be done in Peano arithmetic. As in the relabeling of the natural numbers so that they form this shape. Proving that that is a well ordering is beyond the scope of Peano arithmetic. precisely because so you might have heard that the induction principle is equivalent to the well-ordering principle for natural numbers. It says that every subset of the natural numbers has a least element, or equivalently that you cannot go on an infinite walk in the leftward direction on the natural line. Proving that this is a well-ordering is sort of an expanded induction principle. It's a stronger induction principle than induction with the natural numbers. Which is why it is sort of beyond the scope of Peano arithmetic. Now, this is the part where I start hand waving a bit, because it would not be fair to give the audience the entirety of the proof of why this is beyond the scope of Peano arithmetic, because it involves something about Gödel's incompleteness theorem, which deserves a talk of its own. The idea is this. If you proved that this shape of the natural numbers was in fact a well-ordering, you would be able to prove that Peano arithmetic is consistent. Some hints as to why this is the case is that the same way that we labeled trees in order to show that we could decrease the complexity of the tree every time we deleted something, you can also label proof trees of theorems in Peano arithmetic. The way you arrive at theorems from the axioms. You can label those as well using this specific sequence of ordinals, the sequence of ordinals of the same length as we've used here. And in that manner, you will be able to reduce the proof trees so as to show that those proof trees can never end in, say, 0 equals 1, or 99 equals 100, or that you could not prove any inconsistent statement. And that cannot be done within the confines of Peano arithmetic for the reason of Gödel's incompleteness theorems. Now, I will be a bit philosophical about it. The reason I like this theorem so much is because this allows you to ask a philosophical question in mathematical language. It allows you to ask, can everything about finite objects be known through finite means? And the answer is no, because the extent of finite means is, well, some would argue even Peano arithmetic is too much, but it is definitely captured at least by Peano arithmetic. And this is a theorem about finite objects. It's the theorem about file systems, in our case, or rooted trees. And even though the government can order in principle as much storage as it wants, at each stage, the files that the government has are organized in a finite object. But even so, it requires that we have knowledge of the infinite, such as the ordinals over here, in order to prove this fact about finite numbers. So the reason I wanted to present this is that for people going into higher mathematics, it is important to remember that some 400 or so years ago, mathematics and philosophy and the majority of the sciences were not as separate as they are now. Part of the reason is capitalism, but that's a separate talk. But they're not as separate as they were not as separate as they are now. And sticking to those roots at least a little allows people to ask questions that aren't just of specific mathematical interest, but of general interest, as in of interest about the nature of reason. this is actually specifically what I do. I set theory and logic is sort of my field, and the finding. So the reason I was talking so much about axioms earlier is because theorems like this allow you some perspective on the axioms you have. They allow you so theorems like this tell you what the limits of the induction schema are. They tell you the limits of the concept of induction in a more concrete way by picking apart what the proof trees are for it. And this allows you some perspective into what axioms you should be looking for. Because at the end of the day, when you look at a new axiom, there is no amount of theorem proving that can tell you why that new axiom should be true. Because an axiom is meant to be a self-evident truth. If you're looking at an axiom that nobody has considered before, how do you know it is self-evident without how do you know what is natural to human reason? How do you know what is natural to reason as a concept? Right. And yeah, this sort of theorem allows you to have perspective before you have theorems. It allows you to have philosophy before you have mathematics. So yeah. Actually, I feel like I should be opening. I should be opening the audience to some questions. Or like I should be opening to the audience for some questions because I'm not sure if that discussion would get through to everyone. So yeah, and any questions so far? Yeah.
One small question.
Yeah.
Are the omegas, they're basically just infinities, right?
Omega is one specific infinity. It's the one that sits at the end of the natural numbers.
Right. Right.
So yeah, so as in these are defined essentially by how you reach them. So omega is defined by the fact that you reach it via going through all the natural numbers. For example, omega square is defined by the fact that you reach it by going omega times 2, omega times 3, omega times 4, up to omega square. Yeah. And so just to be clear, earlier we spoke about addition, and addition for natural numbers is fairly obvious, isn't it? Just natural addition. But the same basic principle applies here as well. If you have two ordinals, they are two different points in this spiral, in this line, right? If you translate one to sit at the end of the other, you get their sum. Yeah. Okay. So yeah, I think so. Yeah. So yes, in this manner you will exhaust the file system, the Hydra, etc. And yeah, this discussion of the truth of this theorem and its relation to Peano arithmetic and finitistic reasoning is what I meant by what we know we don't know, because independence results of this natures that that theorems are independent of certain systems of proof or certain axioms. are important to ask, especially about systems like Peano arithmetic, because they're small and useful. Yeah. So I hope I've communicated some interest in what we know we don't know via this talk. So thank you. It's actually a lot shorter than I thought it would be. But yes, that means that there is time for audience interaction if anybody has any questions. But yeah, that's all. Thank you.
Wow, that was great. Yeah. So if anybody has any questions, then ask.
Yeah, so I'm just a bit confused about the part that, like, why is it not provable that there doesn't exist infinite descending chains? Like it should
Yeah.
be
So okay.
provable. Like,
Is it so? It's okay. So I should clarify. It's not that it's not provable. It's just not provable inside Peano arithmetic using those tools. So okay. So okay, I'll try to give you an example of when this happens. So okay. So okay. In this case, the idea is that the okay. So firstly, is the audience the 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 Gödel incompleteness theorems? How much is the audience aware in general of them, about them?
Usually, I would assume not many people, but since I think the
Okay.
audience seems different than the usual one, I can't say.
Okay. So basically, the point is this. So Peano arithmetic onwards, all systems that are stronger than Peano arithmetic um, cannot. It's a slight oversimplification, but they cannot prove that they themselves cannot prove 0 equals 1. Okay. So, in the case of Peano arithmetic, it says that Peano arithmetic cannot prove that Peano arithmetic cannot prove 0 equals 1. Right? And this can be phrased in a lot of ways, but the, the way proof theorists like to phrase it is that if you construct the proof trees for Peano. So, what is a proof tree exactly? So, by proof tree, I mean, for example, if you have A and A implies B, you get B, right? So you can write that as if it's a proof tree. So B is at the bottom, and A and A implies B are connected to it, like this. Or if you want to write it like this, so B is at the top, and A implies B are connected, right? And the leaves are axioms, and you reach a conclusion at the root. Okay. Now proof trees. So now, okay, so the idea is this. So proof trees, similar to trees of this nature in Peano arithmetic. Okay, before getting to that, so the idea is that what we're trying to prove is that no proof tree can end with 0 equals 1. Okay? And the way we do this is by taking a proof tree that supposedly ends in 0 equals 1 and simplify it until we are left with a proof tree that is just an axiom at the top. Okay, we keep simplifying the proof until we are left with nothing in the proof tree except for one node, which is just an axiom, right? And none of the axioms of Peano arithmetic state 0 equals 1. Therefore, 0 equals 1 cannot be proven. That's the structure of the proof, which is that you go from a general proof tree which ends in 0 equals 1 to a very simple one node proof tree which contains 0 equals 1. But that 0 equals 1 should have come from an axiom, which it doesn't. So Peano arithmetic cannot prove 0 equals 1. That is the general structure of these proofs. And the way you do this is by attaching the reduction of the proof tree to ordinals in this manner, very similar to the deletion of files that we did for the government. So the way we simplify the proof tree is by it's a slightly complicated procedure, but it has many similarities to deleting a file and the government making copies. The government making copies actually is there is a very specific analogy. which is that in Peano arithmetic, the crucial step is induction, right? So you have some f0 for all n fn implies fn plus 1. Therefore, and you can use those to imply, say, f32 or f46 or whatever. You can use it to infer anything, right? And you can reduce this um, by removing for all n fn implies fn plus 1 and replacing this with f naught implies f1, f1 implies f2, f2 implies f3, up to f45 implies f46 if you want to get f46. So this is similar to what the government does with I delete one folder and the government makes n copies. There's a very close analogy between the two processes. And the idea is that in a similar manner to how we will eventually exhaust all the files in the government, the reduction procedure for trees will eventually exhaust the entire tree. So if I knew how to prove that this ordering of ordinals is a well ordering, I would have the statement that my reduction of trees eventually terminates at a one node tree, which should contain 0 equals 1. And therefore, I have proved that Peano arithmetic is consistent. I have proved that you cannot prove 0 equals 1 because a single node tree with 0 equals 1 is impossible. This is the part that is bad. As in, using the tools of Peano arithmetic alone, you should not be able to prove that you cannot prove 0 equals 1 in Peano arithmetic. Why that is the case will require a whole other lecture. So I won't get into the details of that, but you can look that part you can look up clearly. Using Peano arithmetic, you should not be able to prove that Peano arithmetic is consistent. If you want, you can look that up yourself. But yeah. And if I do another talk, I will probably do it on the prerequisites theorems. So yeah. I hope that answers your question.
Yeah, thanks.
Yeah, okay, I think are there any other questions? If not, we can end here.
Yeah, I think there aren't any other questions.
Okay.
We can end here.